Welcome everyone to the first screencast in our NLU and information retrieval series. The goal of this introductory screencast is twofold. I will first introduce the IR area. Then I will discuss ways in which NLU and IR can interact productively and focus on how retrieval can be an effective component in defining our NLU tasks and building our NLU systems. So what is information retrieval, or IR? To a first approximation, this is the field concerned with search. The first example that typically comes to mind is web search. But as we'll see today, this field extends richly beyond web search and has strong connections to our work with NLU. Let's now attempt to define IR more formally. Here is a simplified version of the definition used by the Introduction to IR book by Manning et al. They define IR as the process of finding material that fulfills an information need from within a large collection of unstructured documents. Let's unpack this definition. Starting on the left-hand side here, the definition says that we're concerned with finding material from a large collection. In other words, large-scale search is at the essence of IR. On the right-hand side, the definition restricts this to unstructured documents, basically items like text, media, and products, ones that lack the clear-cut structure of things like database tables or graphs. Structure-based search or structure-based traversal of graphs and databases are not typically considered IR problems for our purposes, although, of course, they're interesting on their own right. This leads us to the term that was at the center of our definition, namely the information need. It is difficult to think of IR without thinking of the user at the center of the system. And the information need is what the user has in mind to solve a task or otherwise learn or reach the material that they're looking for. The goal of a search system is thus to identify and fulfill the user's information need. So whatever we retrieve is only going to be considered relevant to the extent that it advances this goal. In most IR tasks, the user will explicitly provide us with a query that summarizes and expresses their information need. It is very important to note that this query may contain ambiguity, may miss some important details, or might even sometimes ask the wrong question, and that's completely normal. The user may not even be sure what precisely they're looking for. That's why they're searching for something. And so we must rely on our knowledge of the task and whatever we know about the user within the constraints of our application in order to solve IR problems. The second thing is that typical information needs vary by task. And so, the typical information need that we have and how to best interpret and deal with that, these are factors that vary greatly by task and by collection type in IR. I'll take it you've already made the connection between IR and searching the web, searching your email, and also finding files on your desktop, buried in deep folders or something. But there are plenty of other IR tasks where search is crucial. For instance, you might want to find recent papers related to the BERT paper by Devlin et al. Now, of course, this is not the best example because there are many, many papers related to BERT these days. But in any case, in this case, your query might be the full text of the BERT paper, and the system might try to search the ACL anthology and the computational language section of arXiv for similar papers to BERT. Recommendation is another key IR topic. In recommendation, we still seek relevant material from a large collection of unstructured items. But in this case, the user has no explicit query. And instead, the previous interactions enable the recommendation system to suggest good matches. Patent search is yet another IR task. And unlike the others we've mentioned so far, it's often used by experts, not by average users, and it has very strong emphasis on high recall. So unlike the average web query, where you might be completely content with one very good match at the top, patent search may need to find every relevant patent to a query or something that approximates that. Lastly, even buying a new laptop can be an IR problem. and in particular, a conversational IR problem. Here, the system may go in a back and forth style between searching for relevant products and asking the user for their preferences about cost, screen quality, and storage, and other factors on online e-commerce platforms. Having looked at all of these IR tasks, it's important to keep in mind that each of those tasks poses its own unique challenges. So even though we're always interested in relevance and in finding relevant items, each of those tasks has its own challenges and its own components. To underscore this, let's use web search as a frame of reference. While standard web search might pose considerable challenge when it comes to the massive scale involved in terms of documents and also queries, even something as seemingly mundane as searching for conversations on your Slack workspace often lacks key features that makes web search tractable in the first place and makes it work the way it does in the first place. For one, so many web searches ask frequently searched or head queries. The sheer popularity of head queries makes them an easy target for large search engines. Of course, there's always a long tail of rare search queries that still pose considerable challenge, especially in highly technical domains. But it still stands that in a domain like web search, solving the head queries gets you a very big share of answering most user queries. As another factor, web search enjoys highly redundant documents out there that address common topics, where each document is written in a slightly different way. This often shifts the search problem into a precision one, basically finding some documents, at least one, that definitely match the query, as opposed to a recall one, finding every document that matches the query, because there's already too many of them. Clearly, this is not always the case if you're looking for a very specific item in your Slack conversational history. Yet another factor in web search is the rich link structure that links between existing related web pages, which again introduces more hierarchy and might make this task more tractable in practice. The idea here is definitely not that web search is easy, because it's not easy, but that the different tasks pose different challenges for our IR systems. So that is IR. Where does our work on NLU fit in IR? Well, of course, queries and documents are often expressed in natural language, at least in part. So we naturally want to understand a query's meaning and its intent, and understand the document's contents and their topics to be able to effectively match queries to documents. This form of understanding is critical, although you can go pretty far for many IR tasks with intelligently matching terms at a lexical level. The vocabulary mismatch problem makes this quite unattractive in practice. To explain, vocabulary mismatch happens when queries and documents use different terms to refer to the same thing. So I have here on the slide an example query that shows this happening in practice. So the question is, or the query is, what compounds protect the digestive system against viruses? And the snippet that we're interested in finding says, in the stomach, gastric acid and proteases serve as powerful chemical defenses against ingested pathogens. You can see that the passage that we found here uses pathogens instead of viruses, which is a bit more general. Stomach instead of the digestive system, which is a bit more specific. And chemical instead of compound. And defenses instead of protect. But it's pretty clear that it still answers the same question, and answers it very well, in fact. So where does NLU fit in IR? I guess a nice quote here is Jamie Lin's statement. Jamie Lin is an IR researcher who says, IR makes NLP useful, and NLP makes IR interesting. Of course, we do think NLP is useful anyway, and also IR is interesting anyway. So I added more between brackets here, but we do get Jimmy's point. Okay, on to our more central question. Where does IR fit into our study of NLU, and how can IR serve us? In thinking about this, I believe it's helpful to appreciate that as our models become more advanced in NLU, they too, like humans, start to have concrete information needs in solving their tasks. More concretely, retrieval can contribute to our NLU tasks and systems in three exciting ways. First, retrieval provides a rich source for creating challenging and realistic NLU tasks, ones where finding information from a large corpus is central. We will look closely at this bullet in the remainder of these slides. Second, retrieval offers a powerful tool to make NLU models for existing tasks more accurate and more effective. We'll touch upon this today, but we'll discuss it in more depth later. Third, retrieval can often lend us a nice framework for evaluating NLU systems whenever the output domain is large, just like in search, or whenever low latency is important, which are key characteristics in IR. We will expand on this in a later screencast as well. In the remainder of the screencast, we'll explore how retrieval allows us to pose very challenging and very realistic open domain NLU tasks. Chris has briefly introduced Squad before in the overview lecture. To remind you of this question answering task, the input that we're given in Squad is a context passage, which was obtained from Wikipedia, and a question that tests our model's understanding of this one passage. This is an interesting task on its own right, one that has enjoyed tons of work and lots of recent progress due to pre-trained language models. But with retrieval in mind, we can move from standard QA, like Squad, to open domain question answering. Specifically, in open domain question answering, we can ask, what if we want to answer the same kinds of factoid questions as Squad or other types of questions, but without the perhaps unrealistic hint of receiving the particular passage in Wikipedia that already contains the answer? In this case, we can take all of the English Wikipedia, just as an example, as our context, and then again pose the same question as Squad over all of Wikipedia, and build models that can answer these open questions over large corpora. So how would we answer such questions? The literature, in particular a nice EMNLP 2020 paper by Roberts et al., introduces a nice analogy for how we might attempt to tackle this task and how we could think about it. The first, perhaps more familiar and perhaps simpler solution is to pose the question to one of our usual transformers, and specifically to a generative sequence-to-sequence model, something like T5, GPT-2, or GPT-3. In this case, we're relying on the knowledge stored internally and implicitly in the model parameters. So the model memorizes these facts, just like you would do when you enter a closed book exam. Often, this knowledge is memorized the same way language is learned as a result of language model pre-training or other similar tasks. Closed book approaches to these characteristically open domain problems offer a particularly consistent way of improving quality and coverage. Well, just take your model, train a larger version of it on more data, and hope that that encodes more knowledge and gives you more accurate results. As an alternative to this, we could think about open book approaches to open domain question answering. So there's the analogy of doing an open book exam, which tests not really your memory, but your awareness of where to look for answers and how to use them quickly and productively. In this case, we would build what are typically called retrieve and read architectures. As shown at the bottom of the slide, we take the question and first feed it to a retriever model. The retriever searches our collection of facts, in this case Wikipedia as an example, and extracts a bunch of passages or other contexts that seem useful in trying to answer the original question. These passages are then fed to a downstream reader. So that could just be a small BERT-like model, which studies these passages to answer the original question. In this pipeline, we've essentially relied on this new retriever component to reduce the original open domain question answering problem to a much smaller scale standard question answering task, where the downstream model sees a question and the relevant passage, or a few passages, before extracting a short answer. Importantly, we could say that the reader in this architecture is a user that has an information need, and it's the retriever's task to satisfy this need accurately and efficiently. We will study various methods for building retrievals in the subsequent screencasts and look at how these retrievals interact with downstream readers. But for now, let us just explore some of the higher level differences between open book and closed book solutions to open domain problems. Our open book solutions often get to be much smaller while being very accurate still. The reason is that we've decoupled knowledge from reasoning and stored the knowledge outside the model. Thus, the model itself does not need to store all of these facts inside its parameters, and it gets to be much smaller as a result. As we will see later, this has great implications for efficiency. Moreover, the knowledge can be easily updated by modifying the collection, as the facts in Wikipedia, for example, evolve over time. Or alternatively, suppose that you want to switch from answering questions over Wikipedia to posing questions over the NLP literature, or perhaps posing questions over the documentation of your favorite software library. You can often do that by simply swapping the collection with a new one and keeping the question answering model as is in order to answer questions in this new domain. Lastly, because we can see the actual documents that are retrieved and the documents that are read by the reader to extract answers, we're often better positioned to explain how these models know some facts or why they make particular mistakes. On the downside, though, all of a sudden we now need to worry about the interactions between two components, the retriever and the reader. But I hope that the subsequent set of screencasts will convince you that working with retrievers in NLU is very rewarding. All of this discussion so far has been in the context of open domain question answering. But there are many other NLU tasks that either inherently subsume retrieval or at least can directly benefit from interacting with a large collection of relevant facts. One of those is claim verification or fact checking. Here, the model receives as input a disputed claim, and its goal is to verify or refute this claim and to return documents that justify its decision. Two other tasks are query-focused summarization and informative dialogue, where we might also work with a large collection of facts and, given a topic or in the context of a conversation, generate a useful summary of the resources about that topic, perhaps as part of a conversation with a user interested to learn about a new topic. Lastly, entity linking is a task that can be posed over a large textual knowledge base as well. Given an utterance that refers to any number of ambiguous entities or events, we should resolve this ambiguity and map dimensions of these entities to their descriptions in a large knowledge base like Wikipedia. So that would be a form of entity linking. KILT, or knowledge-intensive language tasks, is a recent effort aimed at collecting a number of different data sets for retrieval-based NLP. Incidentally, all of these tasks in KILT explicitly have a knowledge component, like answering a question or verifying a claim. An open question in this exciting area is whether retrieval can improve performance for standard NLU tasks as well, ones where the knowledge challenge is less explicit. Think, for example, sentiment analysis, natural language inference, or any of the other tasks we've studied so far. Well, this remains an open question, but I think that accurate knowledge matters for most, if not all, of our language tasks, and that converting many of these tasks to an open book format or bring your own book approach may be a promising way to tackle these tasks in practice. In the remainder of this unit, we will dig deeper into traditional methods and metrics for information retrieval, and then explore recent advances in neural IR, which will make a lot of use of our NLU models like BERT, but in new and creative ways. And then we will finally discuss open domain question answering in more depth as one of the most mature applications of NLU plus IR.